All right, hi everybody. Thanks for coming to this talk. There's an echo. I'm very pleased to introduce Dr. Julia Wellner, who's an associate professor at the University of Houston. Dr. Wellner got her undergraduate degree from Bryn Mawr University and then went on to get an MS from the University of Alabama, and then a PhD from Rice, where she worked with the marine geophysics group, who's been there for a while. Dr. Wellner is very deeply involved in Antarctic research, and her work uses marine geophysics to examine the seafloor in front of ice sheets to be able to interpret their past behavior. Because of the large logistical challenges involved with this kind of work, she's been involved in a lot of very big collaborative projects, including the Larissa project, which was about understanding the collapse of the Larsen ice shelf system. And more recently, she's been leading this project called THOR, which is a great acronym, which is, again, to examine the seafloor in front of Thwaites Glacier. And Thwaites, as many of you know, is one of our most vulnerable parts of the Antarctic ice sheet, but it's also one of the more notoriously difficult places to access in Antarctica. And so leading multiple years of cruises to this location is no easy feat. In particular, she did it during COVID. The first one was there. She was there when COVID broke out and had to come back into the US in quarantine and everything, even though they were already quarantined on the ship for 60 days or something like that. Dr. Wellner is also really heavily involved in Antarctic science community building efforts, both within this international Thwaites collaboration group, where she helps to lead the Inclusion, Diversity, Equity, and Accessibility Council, but also within SCAR, or the Scientific Committee on Antarctic Research as well. So she's a really good person to know in terms of getting into the Antarctic community more general. And my only regret is that I didn't invite her here sooner, which I already admitted to you earlier. So please join me in welcoming her for listening to her research.
Thank you, Ginny. That was a very kind introduction. Can everybody hear me here? Good. I'm very happy to be here, and I appreciate the invitation. And I think you've heard quite clearly what I'm going to be presenting today. I'm going to talk about Thwaites Glacier, about our recent projects there. I'm actually going to share a little bit of the sort of popular news that's covered it, to try to give you some of the reasons that we're studying it. So why all the fuss about tipping points and doomsday glaciers? So for those of you that have never heard it called that, following the 2019 cruise, Thwaites was termed the Doomsday Glacier by a reporter who's actually based here in Austin. And the name stuck. And so what I'm going to talk to you about today is why this name got started, why is Thwaites important, and also maybe at the end, why we shouldn't call it that either. Okay. So what is the International Thwaites Glacier Collaboration? Ginny mentioned this is part of a very, very large project, and that's true. I can't imagine working with any more people on a single group than this. So ITGC, or the Thwaites Glacier Project, involves 8 individual science collaborations, as well as a coordinating office between them. So the coordinating office is for logistics and integration, but each of these 8 individual projects are funded individually. And so we have a group of projects that are working on ice. And so in the schematic, you can see the grounded ice back here flowing out into the ocean. I'll have a lot of schematics like this. I will go into details on a later one. And so there's some projects that are primarily glaciologists and geophysicists working on ice. There are oceanographers that are working in the ocean, as well as installing moorings through the ice. There are projects that are pure modeling and no field work at all. And then THOR, which is the acronym for our project, it just stands for Thwaites Offshore Research. And we are working primarily from the ship, studying the glacial history of Thwaites Glacier. So why is this project here? Thwaites Glacier Collaboration was initiated with the goal of addressing the questions, how much and how fast. Many of you might know this figure from DeConto and Pollard, 2016, that shows the projected contribution to global sea level rise purely from Antarctica's contribution. And so on the bottom, we have years from 2000 to 2100, and on the y-axis, we have change in global mean sea level just from Antarctica. And you can see that there's a range of answers there, going from at the bottom, approximately nothing, right? 11 centimeters, plus or minus 11 centimeters. And then that goes up to about 1.4 meters. That's a huge range. It makes it difficult for coastal planners and communities along the shorelines to plan how much will sea level be rising. Now, I emphasized that this is the 2016 paper. And for those of you that are involved in this type of work, you know that there is a newer paper and the estimates have been lowered. That fits my point exactly, that we don't know. So while these particular authors have now said, okay, it's probably not this high, we're going to aim lower. The point is that if we don't know what's coming, it's hard to plan. And so the Thwaites Glacier collaboration is designed to help control the estimates on this. So what do we know about Thwaites Glacier? First, I just want to emphasize that this is part of the marine-based ice system. And so again, lots of cross sections of ice. Right here, if we take the time to look at it, in the back, we have grounded ice. Out here, we have floating ice. This is the ice shelf. The ice flux coming through here is the key parameter that matters. That's the amount of ice that goes from being grounded to being floating out here over the water. In the ocean, which is relatively cold in the Antarctic, especially where it is in equilibrium with the floating ice, also has warm, deep water that's coming in from underneath. That's warm, deep water helps to melt the ice from the bottom. So the reason we care in particular about marine-based ice sheets is threefold. One, it is grounded below sea level, and therefore it is in contact with the ocean. And in some places, like the Amundsen Sea embayment of Antarctica, we have this warm water coming into the base. Secondly, in many parts, including Thwaites, the bed underneath the grounded ice has this reverse slope. And that means that as the ice starts to retreat, it gets harder and harder for the ice to find its footing, and therefore it retreats a bit more, and then a bit more. And then lastly is that many areas of the marine-based ice sheets have ice shelves. Of course, not all do. There's the Larsen, there's the Ross, there's small floating ice shelves in front of Thwaites. Floating ice has already made its contribution to global sea level, but it's helping to buttress the ice behind that. That was hypothesized for a long time and then really proven clearly following the breakup of the Larsen, when the glaciers flowing into the Larsen ice shelf accelerated following the 2002 breakup. So why the Amundsen Sea? Why are we working here? This is an image showing velocity of the ice around different parts of the Antarctic. And so if we have the South Pole here, of course, here's the Antarctic Peninsula coming up to Chile and Argentina this way. The Amundsen Sea is this sector here of West Antarctica. And we have Pine Island Glacier, sometimes abbreviated PIG, and Thwaites Glacier, which together are flowing into Pine Island Bay and the Amundsen Sea. In the color bar is velocity of the ice, with the yellow colors being relatively slow and the hot red colors being relatively fast ice. And you can see that there's different areas where ice flow gets concentrated into rapidly flowing areas, including a little bit over here in East Antarctica. Some of the major outlets for the West Antarctic Ice Sheet come through here in Pine Island and Thwaites Glacier. those areas are also actively changing. And so again, in the why Amundsen Sea question, we can look at this area and see some obvious ways that the Amundsen Sea stands out. So here, again, in the Amundsen Sea embayment area, you can see a bunch of big red circles, really obviously, surrounding the coastline here. So the circles are representing percent change of ice shelves, where red represents loss and blue represents gain of the ice. And the size of the circle is scaled to the percent change. And out here we can see, obviously, big red circles, and that extends throughout West Antarctica. There's a few areas where we're gaining ice, they're not a lot. And so we can see here this area of focused loss. In this particular image, I'm showing ice shelves. We can show ice acceleration. We can look at mass loss of the grounded ice. There's a range of different ways we can think about this that get us to the same idea of Thwaites being an important area. One additional way we can think about it is a couple different plots of mass balance. So here we just go back to 1980 through 2015 or so, where we have mass balance change on the y-axis. We can see a couple different plots. And this is for the Thwaites Glacier area. I'm not going to worry about the exact numbers. It's always changing, but it's always going down. We're losing ice from this sector, however we look at it. This is an image, sort of hard to see, from Peter Melillo, who's now actually at University of Houston, showing the grounding line or grounding zone migration. So the grounding lines through Thwaites and its eastern ice shelf are stepping back through the satellite era. So I'm still on the intro of what is ITGC. These 8 projects plus the coordinating office came together with the goal of addressing what is happening at Thwaites and how can we understand more. So this is another schematic from the project where you see Thor down here. That's the marine project I'm representing. There's another glacial history project here. There's 4 projects studying the modern ice, 2 that are pure modeling projects. The idea is that each of these projects will be sharing data, integrating, working collaboratively, and that we're feeding each other as well as the paleo community, the wider ice sheet community, and policy and IPCC. If you're interested, there's a couple web addresses down here. There's lots of information about these projects online. So this is the official ITGC diagram. I modified it because really the historical part, I'd like to claim, has relevance to understanding the modern ice behavior. Paleo doesn't just feed paleo. We are helping to feed the understanding of what the ice can do, and vice versa. And I hope by the end of the talk, you will agree with that. The ITGC, as Ginny said, is also active in trying to do community building with a focus on diversity initiatives. This is an intro slide from a talk I gave, purposely showing the bow of the icebreaker that our cruises are on, breaking ice, as a metaphor. We're trying to break through and make some community improvements. We have a large group of people that meet twice a month to discuss community and how we can work together towards the future. We're not always super quick about it, but we are continuing to try. All of our projects include a great deal of outreach as one of those types of efforts for community building. Just within Thor, we've taken a teacher, students, we've had lots of media in our field seasons, social media, etc. This particular thing is just an Instagram story. We've had a series of curriculum developers actually work on Instagram stories, explaining how coring works, how seismic works, how breaking ice works, etc. And this is our team in the 20 cruise. This is on the Nathaniel Palmer. Drones are illegal for most purposes in the Antarctic, but we had a filmmaker on this particular cruise who had a permit, and we were able to get this nice drone shot showing our team. So now I'm going to move into our work specifically through the Thor project. So I have the privilege of representing a huge team of people that are working on the Thwaites marine records. I have 9 co-PIs, some of whom you probably know, like John Anderson or Lauren Simpkins. I'm going to present some work that's been published recently by some of them, and then some work that's in review now from my students. So Thor is aimed at understanding the recent history of Thwaites, and we're doing that by using marine geology and geophysical records. So in this schematic, you can see an irregular seafloor. It's not 4 deep into here. It would be if we scaled way, way out, but it is highly irregular, like the Thwaites seafloor. We have the grounded ice back here that's just gently pinned or resting on a seafloor high, but then has some unpinned areas behind it. It has a floating ice shelf. During the Thor project, we are mainly doing marine work. That includes multi-beam swath bathymetry that I'll show you. We have some multi-channel towed seismic data, which I will not show today. And then primarily what I'm showing is the sediment cores. We took sediment cores during all 3 of our cruises, as well as 1 field season on ice, where the holes were taken, the cores were taken through hot water drill holes in the floating ice. So the reason that's important is we're trying to get a range of facies recovered in the cores. We're trying to get up as close as we can where the ice has just retreated. So of course, our most proximal cores are taken from the ice itself. And then in the marine coring system, we take a range of sediment cores. And together we're reconstructing the ice sheet history, going from the most proximal coarse-grained diamictons, mixed sediment sizes, sometimes over-compacted, high shear strengths, and then moving out, sometimes in the ice shelf area, we have very low sedimentation rates. We're not getting much sediment here, either from the grounding line or from the open ocean. So this is the null zone or slow sedimentation zone. Coming farther and farther out, then we end up with mixed sourced sediments. We have a lot of diatom material, phytoplankton, that's living in the sea and falling and dying there, as well as iceberg rafted debris that gets mixed in with our sediments. So the goals of the project, as defined at the beginning, of course, they morph a little bit over time, but we set out to understand the pre-instrumental or pre-satellite record. You know, satellites were turned on, let's say, in 1970 or so. We have an idea of what Earth has been doing for several decades now. Of course, it's better today than it was in the 70s, but we have some idea. But that doesn't let us know when did these changes start. So a lot of what we're aiming to do is get the record from, let's say, 1900 to 1970 or so. I'm not trying to go back all the way to the last glacial maximum, but rather just get that period just before we started watching so that we're able to understand what kicked off the modern change. With the geophysical data, we're looking for the pathways of warm water. We want to understand the character of the bed. And then what is the role of meltwater? We're getting sediment that is transported out here, not just from subglacial plumes like this or subglacial transport like this, but also from meltwater plumes where fresh water is melting from the underside of the ice and carrying sediment far out into the basin. So that's what we're doing. We've had 3 cruises. So far, we had our early cruise, which was really a trial cruise in 2019. We had the full cruise in 2020. That's the one Ginny mentioned that we extended a little bit as we were quarantined coming home. And then we had a 2022 cruise this year. We quarantined at the start of it instead of the end. And we're back. Our samples aren't even back yet from this cruise. Then in addition, there was the one field season on ice led by James Smith to get the cores under ice. So starting to look at some of our data from this project. Again, our field work is completed. This is just an image. This is gravity-derived bathymetry under ice in the back. And then out here is the marine bathymetry. This is just to show you where we have worked. The white lines are our 2020 cruise, and that's most of the data I am going to present today, because that's when we actually made it to Thwaites for the Thwaites project. Was here in 2020. Excuse me, 2019. The 2020 field season made it to Pine Island and to the eastern ice shelf through here. Lots of work in Pine Island Bay itself, but not directly in front of the prime axis of Thwaites Glacier. And then this year, 2022, in blue, we never made it anywhere near Thwaites or Pine Island. There was extensive sea ice this year, even more than 20, which was more than 19. So this year, we spent the entirety of the cruise at Dotson and Getz A and B. So again, that's going to sort of end up being a separate story. This is partially a separate story, and today we'll focus in here. So what are the data sets we found? So some of you have probably seen Kelly Hogan's paper published in 2020. This is the multi-beam bathymetry compilation from that paper with the 2020 cruise track overlaying. So this is the eastern ice shelf right here. So here are various grounding lines plotted through here. This is Pine Island Glacier flowing from this way out into Pine Island Bay. Eastern ice shelf here, Thwaites Glacier coming out this way. In the background image is the multi-beam swath bathymetry, where you can clearly see the nice images of the seafloor. We had ice flowing out here from Thwaites. You can see the same thing here in Pine Island, paleo flow. These two areas merged in the outer part of Pine Island Bay and then flowed out during the last glacial maximum towards the continental shelf edge. As I said, I'm not really focused on a lot of that right now. We're focused on these very proximal areas where we can see the most recent part of glacial retreat. So this is a compilation image that Kelly led, and it includes multi-beam swath bathymetry from years of work, all the cruises, all the countries that have shared geophysical data is plotted in here. What we were able to add through this project is primarily in the yellow squares. So a little bit over here where Pine Island has recently retreated, a little bit up here. This is Cranton Bay, some very shallow areas where we worked purely through collaborative reasons. We were tagging seals. And so this area allowed that team to work over here. And then this is the area where we were able to access, not previously surveyed seafloor in front of Thwaites Glacier. Kelly and others worked with Tom Jordan in a follow-on paper, also in the cryosphere, that shows the gravity-derived bathymetry compared to the newer multi-beam bathymetry. There are a lot of deep cavities underneath the ice, but one of the results of this project is that a lot of this area in the cavities where we've had very recent retreat, these are relatively small, narrow cavities. That is significant because one of the things that we were doing in collaboration with Anna Whelan from Sweden and the Tarzan team is operating an AUV. This is the autonomous underwater vehicle. Her name is Ron. And this has a downward looking multi-beam or an upward looking multi-beam. Can't do both at the same time. There's also some chirp, there's side scan, there's some water sensors, there's sediment sampling from the water column. This is a really remarkable vessel to send under the ice and get higher resolution mapping as well as water sampling. 2019 was really a test to see how it could be operated and retrieved in ice. This is a vessel, vehicle that, you know, is a few $1 million. And so learning to operate it in these ice and in those small cavities took some working up. So this is the paper Anna led that came out last year and is some of the initial results of those 2019 field seasons. Again, back here is Thwaites Glacier, the grounded ice. Here is the eastern ice shelf and the Thwaites tongue itself over here. And so this is looking at the water column and where is warm water coming up and meeting the ice today. The path of warm water comes from the deep ocean and then follows those deepest troughs up along the continental shelf to reach the base of the ice. And that's why multi-beam isn't just for understanding paleo or geomorphology, but the multi-beam is also showing us the path of warm water flow. And in this cartoon, you know, we use pretty standard colors. So red is going to be hot things or warm things or melting things. Blue is going to be cold or growing. And so we see that there's a couple paths of how warm water is reaching the Thwaites Glacier tongue and the eastern ice shelf over here. So there's deep water underneath the central part that's actually coming from Pine Island Bay. So that's one thing that we note here, is that these glaciers are going to be linked. Pine Island Glacier, which is flowing to the east over here, there's influences with the warmer water coming in and reaching the central part. We also see warm water entering the north from two troughs, and that we have meltwater coming out through this side. I guess you'll admit him. Okay. Okay, so I'm mixing conclusions throughout the talk. This is number 1 of 3 coming. So we have observed, as was predicted, that warm water is reaching the base of the ice here. Ice sheet modeling suggests that the ice can't remain stable for long with the amount of warm water that is reaching it now. But we don't know when this started. So we can tell that the warm water is reaching the base of the ice today. We haven't yet determined how long that has been happening. So that's ongoing work from Thor, where we're looking at diatoms, forams, and trace metals in forams. So a lot of this is being led at the British Antarctic Survey to determine how long ago did this start happening. So looking at some of our other geophysics, we see that we took a range of data types. There is hole-mounted chirp data that collected throughout the cruise. Rob Larder led some multi-channel seismic. And then we also have the Huygens data, the AUV data, which is overlaying here on some of our multi-beam data. So the multi-beam data shown in the larger square, this is just an example of the hull-mounted multi-beam. The best processing we can do still leaves us, with a several meter resolution. And overlaying on that here is some of the multi-beam data from the Huygens, the AUV. And you can see it's a lot smaller, right? If we're moving that right along the seafloor, we can't map very large areas at a time, but we're able to generate these very high resolution images for some parts that we're studying. So some of you I know have seen this paper that came out last week. This is Ali Graham's paper from Monday a week ago, where we're looking at the paleo imprint of the seafloor. What was Thwaites doing to the seafloor in the past? And so this is all data from the Huygens, and you can see these sort of strange tire marks almost in the side scan sonar images. I think, it looks most like a tire or something rolling through sand. But what these ribs are actually paleo grounding lines as the ice was retreating under the influence of a tide. And so this is the cartoon model from that paper, showing how these ribs are interpreted. So the ribs have to be from glacial retreat because they are preserved. If the ice was forming them during forward motion, it would it would destroy its own footprint. And that's why it has to be a death mask. It has to be the features left behind as the ice is retreating. How do we know it's tidal? Well, that's from a spectral analysis of these 160 ribs or so. There is a 14-day periodicity, suggesting that it is in fact tidally driven. And so in this model, we have ice flowing this time from the right to the left. So here is the ice shelf, ocean, and here's the bed. Obviously, this is not to scale because this little cavity here is on the order of centimeters to a meter. And so when ice is when the tide is at low water, we can form this rib here. Sediment is coming out from the base of the ice. Step 2, we go to high tide. The tide lifts the ice up. It steps back, leaving this rib behind. The next time that we reach low tide, an adjacent rib will be formed. So why is this significant? It's not just geomorphology, right? It's not just saying, oh, the ice makes cool images on the seafloor, but the fact that it's tidal allows a timeline to be given. The fact that you can count them, we don't know when they occurred. There is no core from this location, unfortunately. But if we count them, then we get a retreat at something like 2 kilometers per year. That's the spacing and the timing based on that tidal cycle. What that means is that Thwaites was retreating at about 3 times currently observed rates, meaning it can go back much faster than we've ever seen it. So that gets me to conclusion 2, that again goes to our role in ITGC, is that looking at paleo tells us we know the ice can retreat faster than we've yet seen it. We don't know when it happened, but sometime not long ago. So we'd like to then be able to date these things. So now I'm going to get to our core records and show you some of the sediments. I'm going to start with a little bit at Pine Island Glacier. This is another drone shot from our work in 20. So that's actually Pine Island in the background, a little berg that just calved. This is the Palmer, it's 308 feet long. And this was actually the quarterly lifeboat drill. And so that's why you see the lifeboat making a little circle there. So just a moment on looking at Pine Island Glacier. The model from James Smith and others that some of you might know, showing how Pine Island Glacier, Thwaites' neighbor, retreated not long ago. And so this is from sub-ice shelf cores drilled through PIG. So the same hot water system and then sediment cores from below. And here's the grounded ice, the floating ice, the bergs, and the ocean. And then the site of 3 cores that were collected several years ago from this grounding area, which is now, the ice is unpinned from. So these were dated using a few different isotopic systems, including lead-210. Lead-210 is a pretty standard way of dating sediment cores from Galveston or the Gulf of Mexico or Lake Michigan or somewhere like that. Atmospheric lead-210 enters the water column and then is deposited with the sediments. It doesn't get affected by the fact that there's ice here because this is still in contact with the atmosphere, but it shouldn't necessarily be deposited in this subglacial cavity. And so using this lead-210 allowed Smith and others to date the retreat of Pine Island Glacier and find that it pulled back from this ridge sort of in this 1945 to 1970 time period. So lead-210 is what I measure at University of Houston. We have a gamma ray spectrometry system to measure the decay of lead-210, which is a naturally occurring isotope, has a half-life of 22.3 years. So when we measure it, we can get back about 5 half-lives, so about 100 years or so, back to 1900. In my lab, this is the system I have. This is 4,000 pounds of lead, and that shield is not to keep any radioactivity inside, but rather we're measuring extremely low levels of radioactivity. And so we're keeping out the dust and the air you're breathing around so that we measure these very low levels of lead-210. And that allows us to construct age models. In this case, what we see in just an example age model here, the background lead-210 is the amount that's being generated in situ. It's not extra from the atmosphere. And then the excess is the amount of lead-210 that has come from the atmosphere, been deposited in these sediments. If you did this in Galveston Bay, ideally, we'd also have a cesium-137 peak that could be tied with this. Cesium-137 is a bomb product, and we can date 1962 nuclear test ban treaty. In Thwaites, we have not yet found that. We have in the Antarctic Peninsula, but in Thwaites, we seem to be free so far from this sort of nuclear influence. That's nice to know. On the other hand, it is nice when you're able to tie 2 age models together. So far at Thwaites, all we have is the single age model going back down the cores. In 2020, Pine Island did have a major calving. So again, still looking at Thwaites' neighbor at Pine Island. This is Pine Island Glacier here flowing out this way into this area of multi-beam swath bathymetry here. This is the 2013 calving margin, and we show 2013 because that's the year those 3 cores were taken through the ice shelf. In 2020, when we were here, there was a major calving. So the edge of the ice is all the way back here now. And that's the year we took these cores. And this is the first of 2 times. I'm going to show you a time we were able to get marine data where there was previously sub-ice data. And that allows us to compare these facies and compare our methods and our data sets directly at the same location between a marine system and a sub-ice system. Whoops, I forgot to show you the data. So Here in this example, this is KC26, which is the one from the same site that was previously under ice, that we go back and we are able to get back to about 1945 in our age model. And what that shows is the 1970 line, that 1970 change in facies through here is at the same age at the same time as what was previously published. So today I'm not going to talk more about Pine Island. I'm rather just using that as proof that we can really tie from the marine record these short-term records. Okay, we can get these recent ages and have them tie to what we know the ice was doing. So our newest cores, this is the location of the 4 sites of coring that we're collected. There's James collecting cores. These are not yet worked up. These were, of course, done in conjunction with subglacial moorings or sub-ice shelf moorings. And so these sites were not all picked just because they were good places to core, but rather because you could also put moorings down. And so we have to sort of jointly pick those sites. But we also were able to collect about 200 marine cores. That counts all of the different locations together. We collect cores using jumbo gravity core, jumbo piston core. During this cruise, its maximum length was about 6 meters. We also collect cast-in cores. They're much shorter, maximum length about 3 meters. They're much more volume. A lot of the analyses that we do with sediments, we need a great deal of sediment volume, and this gives us the most sediment. It also gives us a higher resolution top than these longer cores. We also collect what's called mega cores. Mega is not for jumbo. Okay, they're the smallest of all our core types. The mega just means that there's lots of them. So this is my collaborator, Becky Totten. And so you can see in this case, that's the entirety of the core, just 20 or 30 centimeters there, but it has water on the top. And so that we're able to get the seafloor water and preserve that interface. So that's an important part of coring. Our cores are then analyzed sometimes on board. So in this case, these are cast-in cores that are being opened on board the ship. Different analyses being done. This is my student, Rachel Clark, measuring shear strengths. Again, shear strength is a proxy for subglacial influence. And in here, we are actually taking pore water samples. These are for Lauren Simpkins students. And the pore water samples, these are just rhizomes that are inserted into the sediment. And then the syringes work for a couple hours to take pore waters out. And the geochemistry records then are used for determining, in part, meltwater activity. As Ginny said, this is a big project, so there's so many different components. We bring these cores in and try to get everything possible out of them. The cores themselves are then actually stored at Oregon State University, which is a US federal repository, where we go and work on the cores and do a variety of post-cruise analyses, as well as scanning. Okay. So I'm going to quickly now step through just a few conclusions based on the cores. So remember that the glacial model that I'm using is that when we're in this really proximal zone, we have these coarse-grained, poorly sorted, maybe normally graded sediments, and the sub-ice shelf, relatively low sedimentation rate, probably pretty fine, possibly laminated. And that in the outer area where it's seasonally open, we start to get the influx of diatomaceous sediments, the phytoplankton, and then IRD. So again, looking at this area, so this is the grounded ice back here. Here is the grounding line, it's not the grounding line, it's the floating ice margin here of the eastern ice shelf. This is the primary area of Thwaites over here. So this is the second time I'm showing you where we have cores, but in this case, we took cores tied to 1978 radar. So Dusty Schroeder published in 2019 some old radar data. That radar line shown here with its plus or minus 5 kilometer for the exact location being unknown. What that means is we took as many cores as we could in that swath so that we're then tying our cores to where we know this ice had previously been pinned. So looking at what we do with these cores, on the far left here, you see a core photo. So this is the top of the sediment core going down 130 centimeters. So this is just one piece of a core. On this area here, we have the core photo. These are line scans, so we get digital color imagery. In the middle, that's that sort of funky gray bar that goes through there. That's actually a narrow X-ray strip laid over the core photo. Our favorite part these days is always getting CAT scans of the cores. These are the same image. This is just false color. This is grayscale. These cores, as I just said, are stored at Oregon State University. These are done at the Oregon State Veterinary School. So they have a CAT scan that you can fit a horse in. And so they fit cores very well. We look, this is calculated density down core, allows us to look at changes. We have shear strength, which I told you is a proxy for understanding subglacial behavior. Magnetic susceptibility helps us correlate between individual cores. It's tied most directly to percent terrigenous sediment versus diatomaceous. Pebble counts. Pebbles come from ice-rafted debris or from subglacial transport, and so we count those individual pebbles. We used to do that just on X-rays, but having CAT scans to do that sort of gives us a much more accurate pebble count than we used to have. These are grain size statistics. In my lab, we also have a laser particle size analyzer. So we do a lot of grain size measurements and statistics on those grain size. And then here you see just stats, water content. Again, that's tied to compaction, but it's also critical for calculating that lead 210 age model. So of course, this is one core. We do it over and over. I'll only make you look at it once. And then we break those into different facies. Our facies are primarily at this point, we're looking at proximity to the ice, as well as the role of meltwater plumes coming out. So now I'll just step through one example area. This is a seafloor high right here. So again, here's Thwaites coming out. The color is the multi-beam swath bathymetry, the core, and then what you'll see in the red dashed line is our interpreted grounded area based on the cores and the bathymetry where it must have been tied at some point. So in the base of this particular core, we have what we interpreted as a little bit of subglacial till. It's not super stiff, but it's somewhat overcompacted. So it may have been not a true subglacial till, but a sort of gently pinned, reworked area of previously marine sediment. Then we step through this proximal glacial marine. It's becoming gradually less proximal as we move up this core. And again, this is just a schematic of the data. You can see here, these triangles just indicate individually finding upwards packages. We get to this transitional facies, which is interpreted as potentially that null zone, the sub-ice area, where it's very slow sedimentation rates. And then at the top of this, we get to seasonally open marine. By the time we get to this seasonally open marine at this point, then we have this much more retreated grounding or retreated floating ice edge as we see it today. So again, if we step through that with multiple cores, we're going to combine those ages I showed you with the facies, with all the different locations. And then this is what Rachel Clark, my PhD student, has in review currently. And so stepping from pre-1940s, I can't put better brackets on that. You know, it could be 1900, it could be 1800, something like that. Could be 1700. We have the grounded area of Thwaites Glacier down here. Here's the edge of the eastern ice shelf and the Thwaites Glacier tongue through here. So in pre-1940s, we interpret that there was grounded ice in these shallows areas here. So in these pinning points or shallows or highs, that we had this area where there must have been more grounded ice than we see today. In the period from 1940 to 1970, and those brackets again are from our lead-210 age models, as well as from where we know there was the radar data coming through, that we have this smaller area of grounded ice based on the bathymetry and known liftoff from our core areas here. And then finally, we get to the modern image where we have the warm water coming in, as I showed you from Anna Whalen's paper earlier. This is that little bit of pinned area that is there today, pinning the tip of the eastern ice shelf on a high out here, where we have our cores in the middle, measuring that retreat. So how is this significant to map these ages? We knew Thwaites was retreating. That's why we went there to begin with. But we only knew that from 1970 or so, based on the turning on the satellites. So from this data, then we're able to say it was before that. We have retreat starting around 1940. I know you can't read all of this data that she compiled down here, but what it tells us is that this 1940s retreat is coincident with what I showed you earlier from Pine Island, that Thwaites and Pine Island began their retreat, or at least their unpinning, at the same time. That strongly suggests to us that their modern retreat is not driven by some internal ice dynamics or some internal behavior, but rather they are being forced by the same forcing mechanisms. And if you look at the broader literature, then it was an El Nino cycle that kicked off this recent retreat, and then modern warming didn't allow the recovery from that. So to link these three conclusions together, we see that there's warm water. Doesn't seem like it can have been there for too long. Otherwise, the ice wouldn't still be there and wouldn't still be stable. We still need to finish our work and tell you when that began. We haven't achieved that yet, but our colleagues are working on it. Conclusion 2 that I showed you from Ali Graham's paper from last week. Ice can retreat even faster than we have seen in the modern. Paleo has a role in teaching us about ice behavior. And we need to date those retreats, and that's what we're working on today. And so this part that I showed you that's still in review down here is that Thwaites and Pine Island are starting to lose their footing or lose their pinning at the same time, which strongly suggests that they are being forced by external drivers rather than one glacier just having some internal ice dynamics. So I started with this. Why do we call it a doomsday? It is retreating. It is a lot of ice. If Thwaites were to lose its footing entirely, a large area of West Antarctic Ice Sheet would then be allowed to flow through there and continue to accelerate and have significant role on sea level rise. Yes, it's retreating. Yes, it's serious. But we also say, please stop calling it the Doomsday Glacier. Actually, this was on Colbert night before last. This has been surprisingly interesting to the general public. We can't tell you why either, why it was so interesting. not that we say, please stop calling it the Doomsday Glacier, not because it's not really serious, but because we don't want you to get too depressed. So please keep studying it and keep thinking about it. And I'll leave it there. Thank you. Okay.
No, you can, I mean, yeah, has anyone got a question here?
Hi, Sean. Oh, no. Okay.
Yeah, I'll go ahead. Maybe this is a quick question. I'm not sure. Maybe I missed it, but when you were talking about those ribs,
Yeah.
and the sort of tidal influence,
Yeah.
those are a spatial distribution, and you mentioned using a spectral analysis.
For the side, the height.
And so, how do you map that to a time scale that tells you about the?
We
that
don't
it's
know when
14
those
days?
happened, right? I have no date for them.
But just the fact that it's tidal means that you
That
can
they're
map
daily.
that somehow from spatial
Mhm.
to a 14-day.
Right.
So how's that done? That maybe I missed that.
Okay. So, right, there's about 160 ribs, and they come in sort of, range of scales, but they are small, 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 bigger. And then, so you have a 7 cycle and a 14 cycle. Okay. So it's the spectral analysis that shows the height comes in 14s, which tells us that they're tidal. Okay. And then if they're tidal, then you can count them and say it's 160 days.
It's not actually a time scale. It's more like a number of.
Yes, absolutely. Absolutely.
I also had a question about Ali's paper.
Mhm.
I was wondering if you have, if anyone looked into like how much of like the sediment could have been from like subglacial, like discharge rates, maybe like within that timing, or like kind of
Like
like
the
the
sediment
breakdown.
flux.
Yeah, kind of like this breakdown of the sediment, I guess, right there that's building up.
Yeah, so that's an interesting question. And, we would love to know more about sediment flux rates in general. I think that particular data set is sort of too small for getting accurate measurements of flux, because those ribs occur sort of in a very small area. And so to get a good sediment flux calculation, we need to integrate over a larger area. And so some people have done that. Phil Bart has worked on that in the Ross Sea, for example. We are working on sediment flux calculations largely from olive Thwaites, not from the subglacial, but from the meltwater. So there's a range of ways. I think assessing subglacial sediment transport rates is really hard in systems like this that are big and open. Where we have the best estimates of rates are places like the Antarctic Peninsula or Chilean Patagonia, where the fjords create sort of narrow closed basins, and you can calculate all the sediment because you can still find it. There's a trap. And here it's so open, it's really hard to get good flux. Sorry.
Thank you.
Yeah, I'm curious about the warm water part. What
Yeah.
was the measurements of the temperature done? I mean, the pathways make a lot of sense, but how warm? And how different from the
Yes, there's
local-
hundreds of CTDs that are included in there. And of course, how warm, it's going to depend if you're measuring it out in the deep water or are you measuring it right at the base of the ice. And so warm is not super warm, of course, and you know that. So it is slightly warm. Looks like there's more to your question.
Well, I was actually curious the numbers, the actual values,
It's about a degree.
just about a degree.
Yeah.
Okay.
Okay.
Interesting.
Okay. You don't need a lot.
No,
Okay. Ian,
Well, thank you, Julia. It's a fascinating talk.
thank
It's
you, Ian.
come a long way since we crudely mapped the former course of the Pine Island Glacier
Yeah.
using the bathymetry of the Polar Sea back in the 80s.
Yeah.
As you know, we've had instruments measuring bedrock change, elevation change, and horizontal motion in that Pine Island
Yeah.
area since 2000, and they're still sending back data as you've been speaking.
Yeah.
And the rates of uplift, as you know, are very high, up to 50 and even 60 millimeters a year. What effect do you think this might have on the pinning the grounding line?
Yeah.
Because we think it's because of the mantle viscosities are rather low there because there's been 200 million years of subduction going on, shutting off in the Cretaceous.
Yes. Great question. And it's a really fun mental exercise to think about how much could isostatic rebound help then restabilize the ice. So I pulled up one of my backup slides while you were asking that question. So yes, this area does have this very warm crust and this low viscosity, and we have this very rapid rebound here. And so this is the 2018 paper, just showing how there's essentially a bullseye in this area of the Amundsen Sea, this very rapid rebound. Of course, it's rapid there for two integrated reasons, because of how much ice we're losing, as well as because of how fast this part of the crust can respond. So I think it's been, as I said before, a really fun exercise to try to think about how much could isostatic adjustment then restabilize the ice. The only people I know that have been thinking about it more than as just a mental exercise are Jeremy Beesis and his postdoc Sam. My understanding is nowhere near enough. You know, that while this is extraordinarily fast for isostatic adjustment, it's not on the same magnitude of the amount of ice we're losing, the amount of change that's happening there. So theoretically, yes, it will help stabilize it. Will it be enough that we'll notice it? No, not necessarily. Okay.
Thank you.
Thanks.
I don't disagree.
Okay, good.
Anyone else? Yeah.
Yeah, I have sort of a more basic question because I'm not a glaciologist. In the beginning, you showed the speeds of the ice and then showed a slide that showed the mass loss. And it looked like the areas where there were higher velocities of the ice, there was less mass loss compared to the area of like Thwaites Glacier that wasn't moving very fast. Is that like a known sort of thing?
So not exactly. So here's, again, just another some of my extra slides at the back. So this one's just closed. So this is, oh, that's heat. Sorry. Well, we don't need a slide. In part, if you were looking at the areas of rapid flow, like into the Ross Sea, they're changing not as fast as Thwaites, but remember those circles were percent for that system. And so the Ross ice shelf, which is huge, it's changing a little bit, but that will, you know, percentage wise, it's not as dramatic. Thwaites today has a very small ice shelf. There's almost nothing left. And so these rapid changes are these big percentages. I think that's the primary part of your question.
Yeah, that makes sense.
Okay. Okay.